In this project, we will numerically validate the results obtained by the paper named CFD Simulation of Flow and Heat Transfer in a Zigzag Channel with Flow Pulsation. As you can see in this slide, we have extracted the figure 1 of the paper, which shows a model of zigzag channel used in the paper. The present model is drawn in 3 dimensions using Design Modeler software. The meshing of the model has been done using ANSYS meshing software, and the mesh type is unstructured. As was mentioned in previous slide about the purpose of this project, in this slide we have brought to you the figure which shows the Nusselt number over Reynolds number, and in this figure you can easily see that we have compared our CFD simulation results with the papers. By clicking on display button, a new window will appear which you can see different parts of your geometry. Now, there are several assumptions taken into account in this project. The first one is that the type of our solver is set to be pressure-based since we are dealing with incompressible flows. Also, as for the velocity formulation, we have taken the absolute formulation for this. And as for the time study, we have selected the steady time study since we didn't want our results to be a function of time. And as it was mentioned in the paper about the temperature of the fluid flow entering the inlet boundary, you can see that this temperature is equal to 293.15 Kelvin. As for 2 wall boundaries defined in this project, both of these walls have stationary wall motion and no slip shear condition. The only difference for these boundaries is in their thermal condition. After double clicking on the residuals button, a new window will appear. In the appear window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. For example, in this slide, we have selected the temperature variable, and then under the surfaces section, we click on our define isosurface, which would be the z coordinate. After that, we click on Save or Display button so that the software will show us the contour. Now in this slide you can see the temperature contour for this range of velocity and Reynolds number, which you can compare with the paper's result. In this slide you can see the velocity contour, which you can compare it with the paper's result. In this slide we have extracted a part of paper's text in which you can see different equations. Equation 6 shows the formula to calculate the Nusselt number. Now in this equation you can see that the Nusselt number requires an average temperature, and that average temperature is defined to be the average temperature of outlet and inlet boundary. Now, as was mentioned in previous slides, we had defined a report to calculate the average temperature on the outlet boundary, and we're going to use this temperature and our inlet temperature and then calculate this average temperature, and then we're going to implement this average temperature in the Nusselt equation in order to calculate the value of it. And finally, in this slide, we have extracted our CFD simulation results and compared it with the paper's result. It should be only mentioned that in this project, we only extracted the Nusselt number for case Reynolds number equal to 191. In order to calculate the Nusselt number for other Reynolds, just have to change the velocity in the inlet boundary settings, and then following the same steps you can extract the Nusselt number yourself. Finally, the summary of different settings and setup that we have used in our project is presented to you in the slide.
Obtain the mesh file and also the full training movie by purchasing this product.
As you can see in this slide, we have extracted the figure 1 of the paper, which shows a model of zigzag channel used in the paper. The channel model is such that the number of stages of channel oscillation in the horizontal direction is equal to 10, and the angle of channel in each of these 10 stages for modeling is assumed to be equal to 15 degrees. Several different Reynolds values, including 53, 107, 191, 266, 320, and 427, were used for this simulation. Therefore, due to the low Reynolds values, the flow in all models is defined as laminar. The inlet velocity of water flow in different models varies based on Reynolds value, but the inlet water flow temperature in all models is equal to 293.15 Kelvin. The lower wall of the zigzag channel is insulated and the upper wall has a constant temperature of 276.65 Kelvin. The main purpose of the problem is to investigate the amount of Nusselt number in the vicinity of the upper wall of the channel. As was mentioned in previous slide about the purpose of this project, in this slide we have brought to you the figure which shows the Nusselt number over Reynolds number, and in this figure you can easily see that we have compared our CFD simulation results with the papers. The present model is drawn in 3 dimensions using Design Modeler software. The present model is related to a channel that has a zigzag structure in its horizontal direction, which is equal to 10 zigzag states. The angle of each of the model's ups and downs with horizontal direction is defined to be as 15 degrees. Also, the width of the channel, or the vertical distance between the upper and lower walls, is assumed to be equal to 8 millimeters, and the depth of this channel is equal to 1 millimeters. The meshing of the model has been done using ANSYS meshing software, and the mesh type is unstructured. The element number is equal to 144,713, and a boundary layer mesh is used on the upper and lower walls of the channel. To benefit from Mr. CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.